Today is the sixth lecture of physical metallurgy. It's October the 3rd. So we'll cover Bainite transformations, a pearlite and Bainite transformation, and then we'll do TTT curves, the time temperature transformation curves for steel. Okay, so let's start with Bainite and pearlite transformation. So I'll draw the iron-carbon diagram. So the iron-carbon diagram has temperature on the vertical axis, percent carbon by weight on the horizontal axis, and we'll only draw the eutectoid portion of the diagram. So it's like this. This is gamma, which is austenite, and this is gamma plus alpha. Alpha is ferrite, and this composition is 0.77% carbon, and this is what we call eutectoid point. This temperature is 727 degrees C, and this phase is gamma plus cementite, Fe3C. So this whole region would be alpha plus Fe3C, and this is alpha. So this is the iron-carbon diagram, just the eutectoid portion of it. So today what we'll do is we'll take this eutectoid composition and we'll heat the steel to say that temperature, which is about 900 degrees centigrade. And then from this temperature, we'll cool the steel and understand how the structure changes as we cool the steel. So when you, so the first step is we austenitize the steel, which means we heat to about 900 degrees centigrade, and then we hold it there so that all the carbon dissolves in the steel, and what you end up with is homogeneous austenite. So you have homogeneous gamma phase, that's that phase over there. So you have a single phase over there, and this would look like if I were to draw a cross section at 900, which nobody can do, but it would look like this. I'm drawing the grains, I'm drawing them dotted. So we call this equiax structure, meaning it's the same in all directions. Any direction look at this. So this is a cross section of austenite. So this is austenite phase, gamma phase, and this is at 900 degrees centigrade. So this is at 900 C. So now what we want to do is to cool it. So as we cool it, as we decrease the temperature, so let's see. So as we cool below 727 degrees C, what happens? So we are in this region over here. You have nucleation. Nucleation of pearlite. So we know pearlite is alpha plus Fe3C, That's cementite. So this nucleation will happen, and it'll happen on the grain boundary. And as we learned earlier, the perlite will grow like this. And so that's one nucleation spot. There might be another nucleation spot over here and so on. So this is perlite. So I've only drawn two, but there can be many, but not too many. And then what will happen is these perlite nodules, so these are nodules of perlite, P for perlite, will grow in size. So two things are happening, nucleation and growth. So these perlite nodules will grow in size. Notice they only grow in one grain. They don't grow in that direction, as we discussed a few weeks ago. Now, what about the rate of nucleation and the rate of growth? So if I were to draw that, so let's draw, so vertical axis is reaction temperature. So that's the temperature over here, over here. So this temperature at which is the temperature of the steel as it's being cooled. So we call that the reaction temperature. And this axis is time. So if I draw the growth rate, no, let me draw the nucleation rate. So nucleation rate is, say, this much, and then it increases. So nucleation rate is, so this is 0. So at this point, nucleation rate would be 0. And then as you cool the steel down, the rate increases, right? So I did this wrong. So this is rate. This is rate of reaction, rate of nucleation, rate of growth. So as the temperature decreases, the growth rate increases. So this is the, did I say growth rate? Let me call this the growth rate. That's the growth rate of the perlite. Growth rate of perlite. And there is a nucleation rate. I'll draw the nucleation rate dotted. So the dotted line is nucleation rate of perlite. So notice that as we decrease temperature, so let's suppose we are at this temperature. So the growth rate is high, but the nucleation rate is very low, right? So let's take the case of, let's say, 700 degrees centigrade. So we cool the steel to 700 degrees centigrade. That's, let's say, somewhere over here, just below the eutectic. At that point, the growth rate will be high, but the nucleation rate is low. So see, I only showed two places of nucleation. So the growth rate will be high, so the perlites will grow. These two nodules, they'll come together. So let me just write over here. What happens at 700 degrees centigrade? So at 700 degrees C, our growth rate is high, our nucleation rate is slow. This should be growth rate is high. So at 700, just below eutectic, growth rate is high, nucleation rate is slow. So I'm only showing two nuclei, and these nodules are very big. So we get few nuclei, but they end up with large perlite nodules. So actually, you can do, if you cool this to room temperature, you can look at the structure and you see these large perlite nodules. So you know that the reaction temperature was high. That means we held it at this temperature for a long time. So now supposing you lower the temperature of reaction, let's say from 700 to, let's suppose, 600. So what will happen? So let's say we have at 600 degrees centigrade reaction temperature, what happens? So let me draw the grains again. So these are the austenite grains. So this is the gamma at 900. So now we're cooling it, and we cool this to 600 instead of 700. So we cool it much lower by 100 degrees. So now what we get, maybe I can just change this to 600. So now growth rate is high, but nucleation rate is also high. So notice in this curve at 600, both the nucleation and the growth rate are high. So we'll have many nuclei, high density of nuclei, and there'll be smaller perlite nodules, because I'll explain why. And the reason is we'll get nucleation all along the grain boundaries. So these are perlites, nodules nucleating, and they'll all grow like this. So there'll be, so many are now growing, each one will be small because they intersect. So we'll have many nodules and they'll be small. So with that, let's go and look at the reaction of the steel. And so we want to get some, so basically we want to heat treat the steel. So for that, we'll learn a new concept. It's called time temperature transformation curves. So what we want to do is to understand the behavior of the steel as we cool from austenite 900 degrees centigrade, we get to the eutectoid. So we want to understand quantitatively what happens below the eutectoid temperature. So let's plot. So let's say we get to a temperature over here, T1. So at T1, let me draw the transformation. So now I'll have log of time on this axis, and on this axis I'll have fraction of gamma that is transformed to perlite. So we start off with zero fraction transformed, and this is 100%. So we started with austenite, and we're transforming that to perlite. So this curve will look something like this. So zero at this point, and at that temperature is 100%. So I can then look at this, and I can take the same information and I can plot it. Again, the log of time, and this time I'm going to have temperature as my vertical axis. So the highest temperature would be 727 degrees C because the transformations happen below the eutectoid temperature. So at this temperature for this curve is T1. What do I get? That this temperature T1 is, let's suppose, over here. So at this temperature, at this point, my transformation starts. At this point, it ends, right? So if I take another temperature, let's say T2, my transformation will start earlier and will end earlier. So I can drop another 2 dotted lines. So basically what I'll get is a curve like, actually, I just want to draw this much of the curve. And so we'll get a curve like this. So what this curve is telling us is that this is the start of the transformation, and this is the end. So at each temperature, so this is T2 and T3 and so forward, so on. So we're doing isothermal transformation. So that's another point to note. So we're doing transformation at constant temperature. So what we're doing is we're taking the steel at 900 and we're quenching it to T1, and then we hold it there. So we can take the steel and drop it on a salt bath. The salt bath is T1. So this is time 0. So and we start observing. At time 0, we still have the alpha ferrite. And actually, at time 0, you have gamma, the austenite. So, and you wait and you wait and you wait. At this point, the pearlite starts coming out. So you have gamma plus pearlite. As you go further down, you have more and more pearlite. At this point, it's all pearlite. So on this curve, you came down from 900, you came to, so you quickly got to T1 and you kept the temperature constant at T1. So you're keeping the temperature constant T1 and you're waiting. At this point, pearlite starts coming out. At this point, it's complete. So now you take temperature T2. So you go to lower temperature. So now the pearlite will come out sooner than at higher temperature, and it'll become completely pearlite sooner. The reason is the curves that I drawn earlier, the nucleation and growth. So at lower temperature, notice as you lower temperature, the nucleation and growth rates increase. So things happen quicker at lower temperature. So that's why as you drop the temperature, these curves are coming to the left. Things happen sooner. So the reason I didn't go any further below this is because below that temperature, there's another reaction that happens, and it's called the Bainite transformation. So this curve that I've drawn is up to about above 500 degrees centigrade, or let's say 550. Let me make it 550. So it's kind of approximate. So up to about 550, we have this behavior, and below that, things change. And the change is that pearlite, let's just discuss pearlite. Pearlite is a mixture of alpha plus Fe3C. So alpha, we call it ferrite. Fe3C is cementite. And basically, you have, if you look at a cross section, you'll have planes of this Fe3C, and they'll be in a matrix of alpha ferrite. So we call this lamellae structure. So these are like plates of Fe3C, which are separated by the alpha. But Bainite is different. So Bainite is, so this is a new component we're looking at, and actually we should not call it component, we should call it constituent, meaning when we polish a sample, we can see the structure. So whatever you can see on the microscope, that particular region is called the constituent of that microstructure. So Bainite is, let me find a new spot for Bainite. So Bainite is not well understood. Bainite is confusing. So Bainite has problems. It's not well understood. It's confusing. There's a lot of controversy. And the problem is Bainite morphology is let's see, very diverse. All kinds of things happen, and Bainite transformation happens over a large temperature range. That's not a concern, but in each temperature range, you get different structure. So it is confusing. So from 500 to 300 degrees centigrade reaction in temperature, we're dealing with isothermal. We have a structure we loosely call upper Bainite. And between 300 degrees centigrade to 200 degrees C, we call it lower Bainite, and they have different structures. So how does Bainite form? So Bainite formation. So the one complication is Bainite can form by two different mechanisms. One is nucleation plus growth, just like perlite grows. So the Bainite is forming from austenite, right? So you have austenite, and what is Bainite? Bainite is also ferrite plus an FeC compound. We'll call it carbide. Instead of Fe3C, it's something else. It's got a little different structure. We'll call it carbide. So you do have a homogeneous structure that goes into alpha, which is almost free of carbon, most of the carbon going over here. So to form the structure, you do need to have diffusion. So diffusion is time dependent. So it's going to take time. Just like the formation of ferrite is time dependent, In other words, at time 0, so you wait and you wait and you wait, then at some time you start getting perlite, and then after a long time it's fully perlite. Similarly, for Bainite, you also have time-dependent transformation. But Bainite also has another type of transformation, and that is athermal transformation. So athermal means that it is dependent on temperature only. So isothermal means is dependent on time, temperature is constant. So isothermal is constant temperature, so the reaction proceeds with time. Athermal means it's independent of time, it depends on temperature. So as soon as you lower the temperature, let's say from 900 you quench down to this temperature way down, the reaction will happen suddenly and it will be only dependent on temperature. So reaction will be slow over here, faster over here, faster over there, faster over there. But it'll be, no, I'm sorry, the reaction will go to completion right away. So at this temperature, let's say the reaction is 0, at this temperature is 100%. So if you quench to this temperature, the reaction will not happen, but a little below, it'll go to 10% completion, 20%, 30%, 40, 100% completion. So the reaction completion depends on temperature. So that's athermal. Whereas if the reaction completion depends on time, then it's isothermal. So this is athermal transformation. Now this transformation is also called martensitic transformation. And we'll study martensitic transformation later, but for the moment assume that it's athermal, means it only depends on temperature, not on time. So notice that we have in Bainite, we have upper Bainite, we have lower Bainite, and then we can have Bainite which is dependent on diffusion, time dependent. It can also be time independent. So it's kind of complicated. Okay, so on this phase diagram, so by the way, this is like a phase diagram, right? So let me draw this little clean. I'm going to use the same space. I'm going to put the Bainite transformation over here. So this is a TTT curve. Here's 727 degrees C. So now I'm going to draw a complete curve. Actually, I can draw a solid line here and a solid line there. So the vertical axis is temperature. Horizontal axis is log of time. So temperature versus log of time. And this is austenite. This is austenite plus perlite. This is perlite. So that exists in approximately that temperature range. So this is about 550 C. Below that, up to about 200 degrees C, this is the Bainite range. So now suppose you take a steel at this temperature and then you quench it down to, let's say, that temperature, and then you hold it there like so. So this is gamma, this will be gamma plus Bainite, then this will be mostly Bainite. And then we already talked about from 500 C to about 300 C, it's upper Bainite. So from 300 to 200C, it is lower bainite. So bainite has two structures, upper bainite and lower bainite. So bainite, we already talked about, is a mixture of alpha, which is ferrite, plus FeXC, we call it iron carbide. So it has a different structure, but it is not lamellar structure, not lamellar. It is basically sort of dispersed FeXC in a matrix of the alpha, which alpha is essentially close to pure iron. So most of the carbon goes into this carbide. Okay, so at this point, okay, so we talked about, let's say we start at this temperature, we cool it down to about, let's say 500, and we do isothermal transformation. With time, the austenite will go into bainite, and then we are here, and we quench down. So we basically, from here to here, nothing happens. So you end up with mostly bainite, right? So suppose, let's do the same exercise, and I come down to this. So we start there, we quench over here, and then we do isothermal transformation, and we then quench from there. We get pearlite. So this path gives us pearlite. So what if I were to come down this path at this temperature? I do isothermal, but I stop over here, and I quench from there. So now what happens is, let's suppose at this point we have half austenite and half bainite. When I quench, this remaining austenite will transform to martensite. We haven't discussed that, but I drew these two lines, and I'm calling this MS, and I'm calling that line, let's see, M, let's say 100. So this is the start of martensite. So let me talk about martensite transformation a little bit. And we'll do martensite in more detail later on. So let's talk about martensite transformation. So martensite transformation is also athermal. So let's take this case where we came down here, we held at this temperature for some time. So now we have 50% austenite, 50% bainite, and we come down, we quench down. So when you get to this point, martensite will start forming. At this point, it'll be more. At this point, 50%. At this point, 80 and 100. So notice, we are not, this is like, time is constant, so we're quenching. So transformation is only a function of temperature. So it's happening as we come down. It's not being delayed, it's instantaneous. But if we just held it over here and we didn't move from this temperature, then only say 20% of the austenite would be martensite. At this, it would be 40%. So this transformation is only happening because of temperature. So martensite is a very, very hard material. Its hardness can be as high as HRC, about 65. So this is hard. H is for hardness. R is for Rockwell. and C is the scale. So we use a diamond indenter. So maybe let me take a minor detour and talk about how do you measure hardness. So hardness is one of the most important properties in metallurgy that we measure. So the way we measure hardness is, let's say we take a piece of steel. So this is the surface, this is a cross section, and we bring an indenter, a sharp object, onto the steel, and then we apply force. Typically, let's say on the C scale, I think we apply 100 kilograms, and this is diamond. So if we have a sharp piece of diamond, we're applying 100 kilogram, and when we do that, the steel gets indented, right? So from this dimension, we can convert that to hardness. We can actually get a number. So martensite has a hardness of about HRC 65, which is almost like glass. It's very hard. But martensite is also very brittle. So if you took martensite, let's say if you take this piece of steel and you make it into martensite. Now how do you make it into martensite? You heat the steel to say 900 C, and then you quench it. At this point, so notice that all along this temperature, the steel is still austenite. It gets to 200, and then it starts transforming to martensite. At about 100, it's completely martensite. So now this is like a piece of glass. If you drop it on the floor, it'll break like glass, but it's very hard. So that's a minor detour. So let's get back to this curve. So let's suppose I start with 900 and I quench it and I end up over here. I get complete martensite, because notice I'm in the gamma range or phase all along until I get here. At this temperature, martensite starts forming, and this temperature is fully formed. So that's martensite. Now suppose, let's see, what else can we do? So just to recap, if I'm here and I come down to this point, I'm still in the gamma, I can go isothermal, form perlite, whereas if I come here, I go this way, at this temperature I start forming bainite, this temperature is formed, then I quench, I get all bainite. In this case, if I come here and I quench, so this portion that is still austenite, when I quench it, that forms martensite. So this would be martensite plus bainite. So these are the various reactions that can happen. Now, we can also do continuous cooling. So far I talked about isothermal cooling, but suppose I take a piece of steel, I quench it, this time temperature relationship might go like this, right? If I cool it fast. So this is fast cooling, and I'll get completely martensite because I avoided the nose of this curve. Now suppose I come down like this, then what happens is that I start getting some perlite over here, I start getting bainite, and then since I'm going so fast, I'm not giving enough time for the transformation, I'll probably get perlite plus bainite plus martensite. If I go like this, then I get all perlite, right? So you can see the power of the time temperature transformation curves. For each steel has its own curve. So from that, you can know how fast you need to cool to get all martensite, or how slowly you need to cool to get all perlite. On this scale, I've not put seconds, right? So this could be 10 to the 1 seconds, this could be 10 to the 2, over here is 10 to the 5. So you can go from seconds to hours on this scale. So that's a description of the TDT curve. And so the last item I think I'll talk about today is, so what good is this stuff for us in practical terms? What do we do with this information? So one thing we can do is there's a treatment called os tempering. So remember I said that martensite is brittle like glass. Now, it can be made softer by tempering it. So tempering means we reheat to, let's say, 300 degrees centigrade approximately. I'm just guessing, for let's say 1 hour. So this martensite gets tempered, and now it gets very tough. So the word tough means it doesn't break. So in metallurgy, toughness means you have to put in a lot of energy to break the steel. So it becomes a two-step process. So to have martensitic heat treatment, you first have to quench to room temperature, and then you reheat to some temperature. I'm just guessing 300 for an hour, and this does the tempering. So this is how you make the steel tough. But there's another treatment called os tempering. And that's a one-step process to make very tough, strong steel. So let's suppose somebody comes to you and says, you want to make a piece of steel which is very tough, very strong, and so it should not be ductile, it should not be brittle. You cannot tolerate brittleness. So you don't want the steel to be brittle. You want it very tough, very strong. Like say you want HRC of 55, which is very hard, but you also want it very tough. So generally, when steel is hard, it doesn't have the toughness, it's brittle. But you want both high hardness and high toughness, then os tempering is a good way to go. And the application for this would be like if you want to make a pistol, if you want to make a gun, if you want to make belt buckles for cars, stuff like that. So you can use os tempering. So os tempering, for that, the first thing you need to know is what is your time temperature transformation curve. So let me draw a fresh curve. So here's temperature, here is log time. So temperature versus log of time, and the curve might look like this. So this is MS, MF. So start of martensite transformation. So this is martensite transformation, and this is the finish, MF, finish of start of martensite and finish of martensite. And so as we already discussed, this is the perlitic region, this is the bainitic region. So bainite forms over here, perlite forms over here when you do isothermal transformation. Now we want to do os tempering. So for os tempering, the word os stands for austenite, and tempering, I don't know where this phrase comes from, but what we can do is we heat the steel to 900 degrees centigrade, we quench so we don't intersect with the nose of the curve, and let's say we bring it here, and then we do isothermal transformation. So this is gamma, this would be gamma plus bainite, and this is bainite. And then we can cool it down to room temperature. So this is os tempering. So you're making sure that you avoid the nose of the DTT curve. You cool it down, quench to this temperature. You hold it at this. Let's say this could be 400 degrees centigrade. So you hold it here, and then you cool down to room temperature. So the way you would do this is you can take a salt bath. You can take a salt which is molten salt at 400 C. So you're basically taking the steel from the furnace at 900 and you're dropping the piece of steel into the 400 degrees centigrade salt bath, and then you keep it there for a few minutes, maybe 5-10 minutes, and then you cool it to room temperature. And the steel you get will be tough, it'll be strong. So you can also make springs. So you can make springs, pistol parts, gun parts, belt buckles. But notice that if you're cooling slowly or slower, you end up over here or you end up over there. So this is no good. So to cool the steel fast, you want to make sure that it's not too thick. It's got to be thin, because if this piece of steel is too big, it takes longer to cool it. So it cannot be too thick. So the steel has to be thin, and so springs can be thin, pistol parts, gun parts are thin, belt buckles are thin. So this technique of os tempering is practical, and it gives you good hardness. You can get up to HRC 55, which is pretty hard, which is very hard. So that's one application of time temperature curves. Okay, on that note, I'm going to stop for today. Thanks for listening.